All right, hey everybody. Sorry for the delay. Let's get started here. Um, and yeah, for today's lecture, I highly encourage you to join the Zoom so you can join the chat. We'll be doing some like live feedback and stuff. So it'll just be kind of fun to be able to type it in either on your phone or directly on your laptop. Um, and I'll be trying to check the chat here too. So we'll try to see how we can use this today to make it a little bit more interactive. Cool. So some announcements. We have homework 5 due Wednesday, and then project 1. So our first project due this Friday, 11 p.m. If you have any project submission issues, please reach out to your GSI. We already had a couple people reach out with some small issues, but just remember to do like one submission if you're working in a group, and make sure that you have your partner listed as well on there. And then we have our midterm in about 2.5 weeks on Friday, 7 to 9 p.m. And so the scope is going to be everything up to and including lecture that day. And really important that you fill out this accommodations form by this Friday at midnight. So this is just so we can get you into like an alternate exam or just figure out your exam time situation in case you have some excuse conflicts. So most people don't have this, but if you're one of the people who needs this, please fill this out. And then I have some new office hours. I mentioned this last week. So everything's on Monday now for me. I have 11 to 12 on Zoom, and then today 5 to 6 p.m. FSM after lecture. So come out to FSM, hang out, and we'll have some office hours there. And I encourage you to come with like any sort of questions you have about like literally anything. Like ask me about career advice, what courses you want to take, what you want to major in. Like I'm happy to help with anything. Don't just use me for data 8. I want to be a resource for you for whatever you need. So feel free to ask me any questions, but just come by. I'll be there right afterwards, right after lecture until like the end of the day. So cool. So what are we doing this week? We're switching goals a little bit or switching gears, not goals. I guess both, and going into probability and statistics a little bit. So we've been doing a lot of Python so far. We've covered basically most of the fundamentals that we need for this course. We've basically covered everything we're going to need to know about how to manipulate tables. Now we're going to go into more probability, chance, and still using Python to do those things, which is where simulation comes in. So that'll be most of today. And then on Wednesday, we'll actually think how do we sample data? What is considered a random sample? What are the kind of best practices there? And then what are some interesting things that happen when you take really large samples? That's going to be very critical to the rest of the course. And then on Friday, we will go into actually modeling data using what we know now about chance and Python, putting that all together to actually model sort of how the world works with math, and then assessing whether what we see in reality actually aligns with our model of the world. So we'll go more into that on Friday. Cool. So firstly, just a small recap of simulation. We like just barely covered this at the end of lecture last week. This takes in together some of the stuff that we learned about how do we randomly choose things. So np.random.choice was something that we covered. We also covered if and else statements, which is how we can choose certain lines of code to be run over others. And then we also briefly covered for loops, which is what allows us to run the same line of code multiple times again and again. And that's really useful for something like simulation. So let's go over here to the notebook. And so for this simulation, we're going to just look at flipping a coin, essentially. So we're going to put our 2 sets of possible outcomes of a coin flip into an array called coin. So I'm just going to run this code. And then the way that we can actually simulate a random flip of a coin is np.random.choice. So we could just go np.random.choice and then pass in our possible choices, which in this case is the array called coin, and we get a result back. And then every time I run this, it's going to do a random flip of this coin. So it's going to randomly choose one of these 2 outcomes. It's going to treat them both as equally likely. So this is essentially like a fair coin. And then every time I run this, it's going to do something different. Sometimes the same result, I guess, because you can get the same result twice in a row. But in general, it's doing a kind of brand new flip of a coin. And so you can see how this changes. And then if you want to do this multiple times, let's say instead of just flipping 1 coin, we wanted to flip 10 and see what happens, we could do that. So I can just add a second argument, let's say 10, and then this will do 10 flips of a coin. And it'll return an array of length 10, and then each element of the array contains what happened for that particular flip. And then once again, if I run this a second time, I'm going to get something slightly different. So in this first run, the first flip was heads, then we got tails, then we got heads. In this case, we got heads followed by 2 tails and then followed by 2 heads. So you can see that's a little bit different, and you'd expect it to be different. And so if you run this on your computer right now, you're also going to get something different. And this is basically how we can do things like sort of just randomly choosing things. And this is really nice because then we can simulate things in the real world. So this is kind of a toy example. You don't really go around flipping into the real world, but there'll be a lot of situations where we work with actual data where we want to actually simulate what would happen if I was like sampling certain parts of the data or just getting certain parts and not seeing all of it. This lets us do that really easily. Another useful thing we can do is we can easily figure out how many of these flips were heads, for example. So if I'm doing, let's say 10 coin flips and I wanted to see how many are heads, one way I could do this is I can take the result of my coin flips and then do equals equals heads. And what this is going to do is it's going to compare every single element of that randomly generated array to the value heads. And it will tell us whether it's actually equal to that or it's not. So maybe to see this best, it might be best to assign this to something. So let's just do like one trial, and then we can just look at the result here. And then the reason I'm assigning it to something is so that it doesn't change around. So we can see the result of one trial. We don't want this to change. I can just put this down here and then see which one is equal to heads. And so as you go through each element, you're going to see that these get converted into true or false. So the first one is tails, that's not equal to heads, so that gives us false. Second one is heads, that gives us true. Third one is heads, that gives us true as well, and so on. So it gets mapped like that. And then once you have it in this form where it's true, false, kind of mentioned before, but if you have an array of true, false, if you just sum up that array, it actually will count how many times you have true in that array. So it's equivalent to just counting up how many times you have true. And so to do that, you could just call sum on this array. And we get 7 in this case. So this essentially means that 7 out of the 10 flips were heads. So this is one way we could do this. And so if you wanted to just do this all in one line, you could totally do that and do like a brand new run. So you could just do sum np.random.choice coin 10 equals heads, and then we get 7. I can do this again. Now I get 4, do this again. So this is going to change around now. But this is just kind of like a fast, simple way to check how many heads we got. And then now that we have the ability to flip a coin, let's say like 10 times, then another thing that could be interesting to do is repeat that process several times. So let's maybe do this for a larger number of flips. So let's say we wanted to do this with like 100 flips, and we wanted to see how often we get heads out of 100 flips. And so here's just like one run of that. So before I do that, and this is where maybe the chat could be useful, try to guess, or just, I'd be curious, like if you can either like raise your hand if you think this is likely or not, but if we did 100 coin flips, do you think like getting 50 out of 100 as heads, is that like a reasonable thing? Like, is that something that would happen? Most likely, yes. Okay, that's fine. You can say that out loud too. What about 80? Do you think like 80 out of 100, is that something that would happen? Yeah, like not that likely, maybe, right? Like might happen, might not, right? One way to think about this is like, let's assume everybody in the class each had their own set of like 100 coins. And so they each did 100 coin flips. And so out of everybody in the class, like how often would you see 80? How often would you see 50, right? Think about that. And then what about something like 99? Like if everybody in the class did this, how many students would get like maybe 99 out of 100? 0, close to 0, right? We don't really know, but it seems like it'd probably be not that often. And so we can actually simulate that process of giving 100 coins to a bunch of people and having them all independently do their own set of 100 flips. That's what we can do with Python really easily. And a for loop is a way to do this because you're kind of doing the same thing again and again and again. So we can go ahead and try to do this in a for loop. So let's first maybe make a function that will let us run the code that we want to run many, many times. In this case, it's counting the results of 100 flips. So I'm just going to call this heads and 100 tosses. So this is going to be my function. And all it's going to do is just run this line of code. And so we can go ahead and just try this out to see if it's doing something reasonable. So we get 51, that's pretty nice. Do it again, 51, 50 again. Now we get something as low as 41 and so on. So it's like moving around a lot. Seems to like 51 a lot, but I think that's just chance. And then now we have a way to do this one time. We can now go ahead and do this many, many times. And the way to do this is with a for loop. So first of all, we'll specify how many simulations we want to do of these 100 coin tosses. So again, we're going to have each simulation is like 100 coin tosses. counting up how many are heads. So we're going to do that entire process 1,000 times, let's say. And so once we know how many times we're going to do this, we can actually run this using a for loop. The way we write the for loop is we say for and then put some name. So typically we'll just do I if we're not actually using the name, and then an array of values. So in this case, we'll do np.arange num simulations. And then what's going to happen in each iteration of the loop is that we're going to run this code heads in 100 tosses. And we want to keep the results. So let's actually create an array called outcomes, which will just store each individual outcome like 47 into a sequence of 1,000. So we can see what happens 1,000 times. And so we can do np.append outcomes, and then the result of a single outcome, which is heads in 100 tosses. And then finally, we can see what happens at the end here, outcomes. So again, just stepping through this code a little bit, the general structure for loop is there's some array of values that we're going to be iterating over in that loop. And then in each iteration of the loop, we're going to assign an element of that array to something. In this case, we'll assign it to something called I. I is just kind of a standard way to do it when you're not actually using the result. On Friday's lecture, there was an example where we were iterating through an array of pets, and we were actually assigning it to something called pet, and we were doing something with it like printing out the name. So in that case, maybe you'd put a name that's more descriptive. But in this case, we're not actually doing anything with I, so it's okay to just call it something simple. And then this will basically just do this line of code 1,000 times. That's effectively what's going to happen. And so if we go ahead and run this, we see that actually outcomes is empty here. So any guesses as to why this is empty when we just did this 1,000 times? Yeah. Yeah, so outcomes is never reassigned. The way np.append works is it will take whatever is in outcomes, take the result of heads in 100 tosses, which is just a single number like 47, put them together, and then return a new array. So it doesn't actually modify that original array called outcomes. So a little bit tricky. So we have to make sure to assign this back. This is going to be a common mistake that happens all the time. That's totally okay, as long as you know how to catch it. That's the most important thing. And so the way to fix this is assign this back into outcomes. Now outcomes will get bigger every single time. It goes through a loop in the iteration. So now we can go ahead and run this, and then now we get a bunch of outcomes. So that's great. So that's exactly what we wanted. And so now we can see kind of all the numbers. So we were talking about some numbers we mentioned like 50, 80, 99. So you can see like how often some of these numbers are actually coming up. And so it's nice to actually see this in this format, or maybe it's not nice, but it would be nice to put this in a chart, like we can put all the values into a table. That's kind of the first step always. So let's just call this the heads table. And what we'll do is this is just going to have a single column. We'll just call it heads. And in it, we're going to pass in the array we just created of 1,000 different outcomes. And then we can go ahead and plot a histogram of this. So we'll do heads.hist. Which column are we doing a hist of? Well, it's just heads, only one column, but we still have to specify it. And then what bins do we want? I'm just going to go ahead and put some bins here based on a range of values from roughly 25 to 75. And so if we go ahead and do this, then we get something like this. So you get this nice looking histogram. It's like centered at 50, which we kind of all thought was going to be a really common value. Sometimes you get as values as big as 60 or 40. Turns out we don't actually get anything really close to 80, which is surprising. We kind of would have thought maybe 80 would have come up, but turns out with 100 tosses, 80 is just not that common. There's still some chance of getting 80, right? But it's very, very small. It's like really close to 0. Maybe if you did this simulation like 1 million times or like 10 million times, then maybe you'd start to see something at 80. But in general, it's just not very likely. So any questions about this example? Yeah. Is there a name for this distribution? Yeah, we'll go into that, I guess, a little bit later in the course. But yeah, there's certain distributions have different names, yes. Yeah. Oh, in the outcomes array, why are the values floats? This is a good question. So I believe it's because when we initialize an array like just empty without specifying values, I think it might default to just floats as arrays. That would be my guess. Because yeah, the heads in 100 tosses we can see here, that's actually just generating as integers. but that's going to be my guess here, is that if you just make it blank, it's kind of like assuming that you're starting with floats. It's typically the safer way to go. And then, it's more flexible, I guess, than integers. Yeah. Yeah, so the for loop, what's happening here is it's going through every element of the array that you specify here. So np.arange num simulations, that's an array from 0 up to 999. Okay, so that's the array of values. And then what this for loop is going to do is it's going to step through every single value. So the first one, the value is 0. It's going to assign I to 0. Then it's going to run this code below. Then it goes to the next one. I equals 1 now. Run this line of code. I equals 2 now. Run this line of code all the way to I equals 999. That's generally how for loop works. In this case, we didn't really do anything with I, but we do need to specify some sort of name there. Yeah. Cool. Awesome. So we'll be using this sort of technique again and again and again for the next like 6 lectures, I would say. And it's really just always going to look like this. So it's like, we're trying to do this thing. We're trying to simulate it many, many times. Let's do it for a loop. Let's just run that same thing again and again. Let's make sure we store the results because we want to see those results in some sort of visualization later. And so it's kind of combining, the last few lectures, really, charts and tables and also for loops. Cool. So that's simulation. We'll be doing a little bit more of that today. Now, before we go back into some of the Python, I do want to cover a little bit just about chance and probability. You can think of these things basically sort of like interchangeable. So some basics about probabilities. The lowest possible value you can have probability of something is 0. So if I say that, what's the probability that if I pick someone randomly in data 8, that they're from Mars? So that should be 0 ideally. So it's like lowest possible value. So 0 means it's just impossible. And then at the same end, if you have at the very highest end, the probability is 1. So if I pick somebody randomly from data 8, probably that they're from Earth, 1. So 100%. And so that chance of that event is certain, or you can just say the event is certain. That's also fine. Equivalent statements there. So that's how we think about probability. So they always have to be 0 to 1. So you can't say like chance of this is 110%. That doesn't work. 100's the max. You can't go more than that. And then you also can't have negative values. So we just have to have some rules around probabilities defined here. And then one kind of common statement is if you have some event and you're trying to figure out what's the chance of it happening, the complement is essentially the chance that the event does not happen. And this is very useful because a lot of times when you're trying to calculate probabilities of some events, they're kind of complex and hard to figure out. But it turns out the chance of them not happening is like a bit easier to figure out the probability of. So we'll find that probability first and then subtract it from 100%. So if you know that an event has a chance 70%, then the chance that it doesn't happen is just 100 minus 70, so 30%. And so this is just, again, going with the rules that sort of like the chance of anything sort of happening needs to be 100 when you're talking about some sort of events. And so it's like either the event's going to happen or it's not going to happen. And so that's why the sum of both of those things needs to be 100%. And so this allows us to calculate probabilities of complements easily. And then another way to kind of actually find probabilities of events, if you're trying to actually solve a probability problem, which we're going to do a few of today, is if you know that sort of all the outcomes that could happen are equally likely, such as flipping a coin or like rolling a die, all the different outcomes like 1 through 6 on a die or heads or tails on a coin are equally likely, then the chance of any particular events happening is just the number of outcomes that make event A happen divided by the total number of outcomes. So for example, if you have like a die and you're saying, what's the chance of rolling something that's even? So if I wanted to calculate that, I could go out and say, okay, well, let's see how many outcomes make something even happen. Well, I could have 2, I could have 4, I could have 6. So it's 3 possible things. And then on the bottom, there's total number of outcomes, all possible things, 6. So 3 out of 6 gives me half, right? So you didn't really need to step through it that way because you kind of probably figured out the answer quickly, but it's just a way to think about these problems when you have something more complex like that. You can kind of break out your event into all the different ways that it can happen, which are called outcomes. And so with that, we can try to answer a question that's a little bit more complex. So let's say I have 3 cards in a deck. So it's a really simple deck of cards, just 3: ace of hearts, king of diamonds, queen of spades. The suits actually don't really matter. So ace, king, queen basically is the most important thing. And what we're going to do is we're going to shuffle this deck of 3 cards. We're going to take 2 cards out of it at random without replacement. So without replacement basically means I take out one card as my first step. I don't put it back. I just put it to the side. Now I have 2 cards left. I take out one of those 2 cards. So without replacing it, I take out 2 cards. And so if you're assuming you're doing this, what is the chance that you get a queen followed by a king? So a very specific statement here. We're going to get a queen on that first card, put it to the side. Now we have 2 cards left. We draw a card. It's a king. So that sequence of events happening, what's the chance of that? And so we could try to answer this question using the equally likely outcomes sort of methodology, which is we could actually just write out all the unique ways that we can have different events happening, and then figure out what are the unique ways of having this particular thing happening. So I'll just zoom in a bit. Sorry, add a few cells here. So if we wanted to just write out all the possible things that could happen, we could actually just list them out. So one possible thing is I could get an ace on my first card, move it to the side. Now I have king and the queen left. Maybe I pick a king. That's like one possible thing. Another possible outcome is I could get ace followed by a queen. Another possible outcome is I could get queen followed by a king, or I could get queen followed by an ace. And then I could also get a king as a first card followed by an ace, or a king followed by a queen. And so as you write these out, we basically find that like these are the only possible outcomes that we can get, because the order also matters, right? So queen followed by king is different than king followed by queen. And so there's basically 6 possible outcomes that can happen here. And then the event we're looking for is queen followed by king. So there's only one possible outcome that actually leads to that event happening in this case. And so we can figure out pretty quickly now using the equally likely outcomes approach that the probability of this event is 1 out of 6. So there's like 6 possible things that could happen, but only one of them is actually leading us to the event that we care about. So that's one way that we could calculate this. Another way to think about this is to think of it sort of in steps of sort of different events that have to happen one after another. And that way of thinking about things is a little bit better, because if you had like a lot of cards, this would get pretty complicated, right? Like we were able to write out the 6 different ways this could happen because we just had 3 cards. But imagine we had all 52 cards in the deck and we were trying to draw 2 cards out of it, and you wanted to list out like all the possible ways you could draw 2 cards. That's a lot of possible outcomes there. And so it'll take you a very long time to do that. And so this isn't really the best approach always. And so in that type of situation where you might have like a lot more cards, it's better to split it up into 2 steps. So maybe like our first step would be, okay, we are drawing 1 card off the bat. So let's just try to see what's the probability of getting a queen on that first step. So I can just write out the different possible outcomes. It's just ace, king, queen. That's really easy. And so the probability of getting a queen in the first step, well, that's just 1 out of 3. And then similarly, we could do the same thing, but as the second card. So I've taken, now I know that I took the queen out, so I'm just going to box it here. So I've taken the queen out. Now I just have 2 cards left, ace and king, and I need the king to be my second card now. So what's the probability of getting a king now that I only have those 2 cards left? It's going to be 1 out of 2. We can see that really clearly here because it's just 2 choices. And if you break it out in this way in terms of steps, so this is kind of like first card, and this is second card. If you break it out into steps like that, what you can do is you can actually multiply the probabilities together. That's the way probabilities work. So if you have like event A and event B happening, given that we know A already happened, I can just multiply those probabilities together. And so we can do 1/3 times 1/2, and that also gives us 1/6. So you get to the same answer, but it's just a slightly different way of doing it. But it turns out that this second way of doing it, where you break it down to 2 steps and multiply the probabilities, will just work better for a situation where you have, like, let's say 52 cards. You could do the same exercise and you'll find that it's a lot easier to figure out the answer in like a full deck versus like a deck of 3 cards. So these are just like 2 different approaches that you could take to calculate probabilities. Just kind of depends on which one works better. And typically, if you don't have that many options to choose from, you already know off the bat it's not going to be a lot. You might as well go ahead and just try this approach on the top and just write things out really explicitly. And this second approach that we just did is actually like a name for it. It's called the multiplication rule. And basically what it's saying is the chance that 2 events A and B, so in this case, like getting a queen followed by a king, the chance that both happens is the probability that A happens. So probably I get a queen on the first card times the probability that B happens given that A happened. So the probability that I get a king on the second card, given that the queen was the card that was already taken out of the deck. So very like explicit statement that you're writing there. And one thing about this approach, and this is just a good kind of check for you when you're doing the math here, is that the result of this multiplication should always be less than or equal to each of the two individual chances that are being multiplied. And the reason for this is because chances are at most one. They can't be more than one. So if I have something that's like at most one and I'm multiplying by something else that's at most one, this next thing can't be bigger than either of those values. It's going to have to be less than both of them. And one way to think about that just intuitively is A and B are like two different events that I want to happen. And it's very restrictive if I need both of them to happen. If I just need A to happen or I just need B to happen, you'd expect those things to be bigger than the situation where I need both of them happening. That's more conditions that I'm adding to the statement. So it should be harder for it to happen. Therefore, probability should be less. So that's how we can use the multiplication rule. And it's just good to check that when you're actually doing the math. Like you should be expecting this to get smaller as you're multiplying probabilities. Yeah. Do they assume that the probabilities are independent of each other? I mean, I guess independence a little bit beyond the scope of this class. But one assumption we are making is that we already know that A has happened. That's the key here. So we know that A has happened, and we're saying that B must happen now. So that's a pretty explicit statement. We're not just saying like B happens. Like we're not just saying like king is a second card. We're being very clear in saying king is a second card, and we already know that queen was taken out. Right. So the math only works if you assume that. Cool. And so one other question that we could try to consider is same set of situation where we have those three cards, we shuffle it, we do two cards without replacement, and we ask, what's the chance that one of the cards I draw is a king and the other one is a queen? So we're not saying anything about order here. So like I could get king followed by queen or vice versa, but we're just saying that I want to get a king and a queen in some sort of order. What's the chance of this? So again, we could take a similar sort of approach, which is we could try to write out maybe, well, I guess we can think about actually the last two approaches. So we can either try like equally likely, or we can try to do the multiplication thing. So if we wanted to do the multiplication thing, then we'd have to figure out a way to calculate the probability of some sort of thing happening on this first card and then something else happening on the second card, given what happens on the first card. But that gets a little bit complicated because the first card could be either a king or a queen. So there's like two possible things that could happen. And the probability of what's happening in the second card sort of depends on which outcome we ended up going in. So there isn't really like one clear event that we're talking about necessarily for that first card. And so in that case, it's maybe a hint that we should try to split it out into equally likely events and just look at what are the possible options there. And so we could go ahead and try that. So we could actually write out sort of all the possible things that could happen. So let's maybe talk about one way that we could get a king and a queen. So one way would be that on the first card, we get out of ace, king, and queen, we actually draw the queen. And then on the second card, we have now ace and king left over, and we get the king this time around. So that's like one possible way that this could happen. And then another possible way is basically the opposite. So we get the king on the first try. So I'm just going to put brackets around that. And in that case, what's going to happen is when I go to my second card to draw it, now I have the ace and the queen left over. And we need to get the queen out of that set of cards. So just notice the two different ways here. And so notice these are quite different because in this case, I get the queen first. Now I only have the ace and king left over. In this case, I get the king first. I have the ace and the queen left over. So, but we can still calculate probabilities the same way. And so if we wanted to calculate the probability of this first way of this event happening, we already know how to do this from above. 1 out of 3 chance of getting a queen, followed by 1/2 chance of getting a king. So this is just going to be 1/3 times 1/2. And then if you go down here, it turns out this one's also calculated the same way. So king on the first card, that's just 1/3. And then queen on the second card, that's just 1/2 again here. And so both of these are 1/6, which is interesting. And because these are two distinct ways of this event happening, remember the event was just get a king and a queen. So if you have two distinct ways of this happening and you can calculate the probabilities individually, you can just add them together to figure out the probability of either one happening. So either A or B happening is just probability of A plus probability of B if they're two distinct things, meaning that like they can't both happen at the same time. And so if you just go down this chain of events, these both can't happen in the same. There's no overlap in terms of like the sequence of things that happened. And so the total probability would just be 1/6 plus 1/6, which is going to be 1/3. And so we're allowed to do that. So it's sort of like the opposite of the multiplication rule. Instead of saying like event A and event B, here we're saying event A or event B. So it's like either things happen this way it's going to happen this way. And so that's a case where you can add probabilities together. And so just writing this out explicitly, we call this the addition rule. And so if event A can happen in exactly one of two ways, then you can write its probability as a probability the first way plus probability the second way. And in this case, we're adding two things together. So the answer should be greater than or equal to each of the individual probabilities because we're adding two things that are both greater than 0, right? Cool. So any questions about that example? Yeah. Yeah, for sure. Does it work with more than 2 events? Yes, you can totally do that. So you could have 3 events. You just need to make sure like they're all distinct and there's like no overlap and like this. But yeah, you can do that too. Cool. So last one I'll just cover is the complement rule. So we talked about complements. I mentioned how sometimes complements are useful because it's like kind of hard to find the probability of something, but it's really easy to find the probability of the opposite of the thing that you're looking at. So for example, let's say that I'm going to do three tosses of a coin, and I want to see the probability of getting any outcome except for this one. So tails, tails, tails is the outcome I don't want. And I'm okay with like all other possible outcomes. I can get 3 heads, I can get a head followed by 2 tails, like all the possible things you could think of are all there, right? And so if you're trying to figure out the probability of like all of those other things, it starts to get kind of complex as you start to think about it. There's just like so many other possible things that could happen. If you try to go equally likely approach, there's just like way too many. If you try to think about it in like sequences of things, maybe you could try to do it that way too, but it gets a little bit tricky. But if we were to do the multiplication rule, we could do this. So we could say, okay, probability of tails, tails, tails is 1/2, 1/2, 1/2, because they're all, each coin flip has no impact on the other. And so I could just do 1/2, 1/2, 1/2, I get an eighth. And so therefore the probability of not getting tails, 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 which is what we were originally looking for, is 1 minus that, which gives us 87.5%. So just again to recap, if you were concerned with, let's say, the probability of getting at least 1 head, which basically means like any outcome except for all tails, at least 1 head on its own is like pretty tricky to calculate. But it turns out that the opposite of that, which is just tails, 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 that's really easy to calculate. And so we can just calculate that one instead. In this case, you get 1/8. And so it makes the math a little bit easier for you. This one, for example, is really hard. Like at least 1 head, if you were trying to think about this with the multiplication rule, you wouldn't really be able to do this. Because that first flip, like maybe I could have a head, maybe not. It kind of depends. Like I'm okay to have a head there, but I just need to make sure like then the rest of them could be like anything. Or if I don't get a head on the first one, then I need to make sure I get a head somewhere along the way in the later ones, right? It gets kind of complicated to do it with the multiplication rule. And then similarly with the equally likely outcomes also gets kind of tricky because it's just like so many possible things that could happen with 3 coin flips. But this is just kind of the easiest way to do it. And then if you extend this to like 10 coin tosses, you'll see like this is where it's even easier to do it. So if I had 10 coin tosses and I want to know the probability of at least 1 head, again, here, it's going to be really challenging to do this and think of all the different ways that I could get at least 1 head, but we can just flip it on its head. Sorry, I didn't mean to say head, but just flip it around and, all tails, right? And so it's like, okay, that's easy. All tails is just 1/2 to the 10th power because 1/2, 1/2, 1/2 all the way down. And I can just subtract that. And so it turns out probably getting at least 1 head in 10 tosses is like 99.9%, which is kind of interesting. So this is how we can use complements. So in general, sort of the process when you're trying to go through these probability questions is to ask yourself what event must happen on the first trial. So if you can break it out into like steps, so trial steps is kind of like first card, second card, try to think about what needs to happen on that first step. And so if there's a clear answer of like what happens in that first step and you can calculate it easily, then you'll probably end up using the multiplication rule. But if there's no clear answer as to what's going to happen in that first step, then maybe try to just list out all the distinct ways that your events can happen and try to add up their chances. And then finally, if you try to list out the distinct ways and you start to realize like, okay, this is just getting crazy, there's way too many ways this can happen, then sort of like last resort is to just do the complement rule. So it's like, okay, I've given up, like I've already written out 10 different ways this can happen and the list keeps getting longer. Let's just try to look at the complement. Maybe that's going to be easier. And so when you go look at the complement, start again from the top. So, okay, let's look at the complement. Let's see if we can break this out with the multiplication rule. Let's see if we can break this out with the distinct ways. And then hopefully we can find an answer in one of those 2 ways. So that's kind of the way to go about trying to answer these problems. And so this isn't something that you need to like memorize or anything, but it's just a good sort of guideline to follow, I think, when you're doing these problems. So let's try to do a discussion question together. It's a little bit harder. We'll spend maybe like a couple minutes on it and see if we can come up with the answers together. So we have a population of 100 people, including Rick and Morty, and we want to sample 2 people at random without replacement from this population. And we have 2 questions here, so maybe we can just focus on the first one. So if I'm sampling 2 people at random without replacement from this population of 100, what's the probability that both Rick and Morty are in the sample? And then the second question is probably that neither Rick nor Morty is in the sample. So try to work on this for a couple of minutes and then we can go over the answer. Okay, so let's try to go over these. Don't worry if you didn't get it in that amount of time, but we'll go over it together. So for the first question, we have probably both Rick and Morty are in the sample. And so this is actually quite similar to the question we were doing with the queen and the king. We need both queen and the king to be in there, right? And so in that situation, we were able to think about just doing these in terms of like steps, maybe. But before we even do that, maybe it's just good to think about what are the ways this could happen, right? So I just have a sample of 2. So like one way this could happen is like I get Rick first, then I get Morty. Another way this could happen is I get Morty first and then get Rick. And so those are 2 completely different, distinct ways of this happening. And so I could split that out and try to calculate the probability of each one, right? And so if you want to do the probability of just one of those things, like let's say getting Rick on the first one, that's going to be 1 out of 100 because there's 100 possible choices. One of them's Rick. Once we take him out, now there's 99 people left, and I need to get Morty in the second one, so 1 out of 99 for the second. And so that's how we can calculate the probability of one way of this happening. But you have to remember there's 2 ways of this happening, so it's a little bit tricky. So we have probably first Rick, then Morty, and then the second probability is first Morty, then Rick. Each of those probabilities is actually the same, 1 out of 100 times 1 out of 99, but you need to add them both together because there are 2 distinct ways of this happening. And so this is what we get as our answer. And then finally, for this second question, probably neither Rick nor Morty is a sample. Basically, we just need both of them to not be in there. And so for this one, we don't actually even have to use the complement rule. We could just think about it in steps. So on my first step, I need just to make sure both of these 2 people aren't picked. So any of the other 98 people can be picked. So 98 out of 100 on that first step. All right, now I've taken 1 person out. I have 99 people left. But once again, I need to make sure those 2 aren't picked on that second step. So now I'll be 97 out of 99. So if you write this out, we'll get it like this. So again, this first one is 98 out of 100 because I need any of the other 98 people besides those 2. And then it's the same logic for the second step, but we have 1 less person now because they got taken out already. So that's how we do the math for that. Cool. So that's how we can do that question, or both of those questions, I guess. And then last thing I'll end with is the Monty Hall problem. So you may have heard of this already, but this is from a game show. And so the way this works is you have 3 doors in this game show that you can choose from. And there's a car behind one door, and then the other 2 doors have goats behind them. And so you want to try to get the car, assuming you really like cars more than goats. And so what's going to happen is you get to pick a random door because you have no idea. Like you're just going to pick a random number. Maybe you pick your favorite number or whatever kind of scheme you want to use, but you pick some sort of door. And then once you pick that door, the host is going to reveal a door that has a goat behind it. And once they reveal that, then they ask you, do you want to switch to the other door that you didn't pick? Or do you want to keep your original choice? So for example, let's say that we picked the first one just randomly. And then the host shows us that actually there's a goat behind door number 3. Do you want to now switch to door number 2? Or do you want to stay at the same place? So any guesses, like, does it seem like, how many people think that it's better to switch? And how many people think it's better to stay? And how many people think it doesn't matter? Like it's kind of the same, like 50-50 either way. Yeah. So it's tricky, right? It seems like it might be 50-50 because it's like, well, I could just go either one. But what's interesting is that there's 2 goats behind these doors. So like you already knew there was going to be a goat here in one of these other 2 doors. They just gave you some extra information by telling you which one it was, but you already knew there was a goat there. It actually didn't change sort of the sequence of events. And so it turns out that switching is actually better. And the easiest way to see this, I think, is to just look at this in terms of equally likely outcomes. So let's just go through this really quickly. So your choice initially could have been one of these 3 things. So either let's just call it goat 1, goat 2, or the car. You picked randomly one of these 3 things, okay? And so let's see what Monty, that's the name of the host, what he would have revealed based on your choice. So if you chose the goat 1 as your initial choice, his only option is to show you the door behind goat 2. He's not going to show you the car, obviously. And then if you chose goat 2, his only option is to show you goat 1. And then if you chose the car, both of the other 2 doors have goats. And so he's just going to randomly pick one. It doesn't really matter. But he's going to pick either goat 1 or goat 2. And so given that he's done that, now let's take a look at what's left behind the remaining door if we were to switch. So if we were to switch in that first situation, we picked goat 1, goat 2 has been revealed. That means there's a car in the last door. Second situation, we picked goat 2, goat 1 is revealed. That means there's a car behind that, the remaining door. And then finally, if we pick the car, some random goat was shown to us, which means obviously the other door has a goat. But fundamentally, look back at the beginning here. These were our choices. Each of these has a probability of 1/3. And what he's going to choose, he's going to choose. But you can see clearly now that like if these are the 3 possible outcomes for me, then the probability of actually getting a car if I switch is 2 out of 3. So it's actually better to switch. If you stayed, then you're most likely not going to get the goat, or most likely not going to get the car. The chance of getting the car is actually just 1 out of 3, but it basically doubles if you switch. So it's a little bit weird, but I think this visual makes it a little bit easy to see. And we do have a Python demo, which hopefully we'll be able to get through in the next lecture, but it shows you the proof of this using simulation. So we simulate a game several thousands of times, and we'll see that switching is actually going to be better 2 times out of 3. Cool. Thanks.